Okay. Hi. Hello, everyone. Thanks for being there today. I'm going to present Quokka. So first, I'm going to talk a bit more about myself. I'm, as Phil said, a security researcher at Quokka, and since October, I defended my PhD, and the stuff I'm going to present today is something I did during this time. And I'm working at Quokka, which is a security company, and we also publish some internship. So if you are looking for an internship, don't hesitate to look at our offers. So first, let's introduce a bit more what is Quokka and what is it useful for. And for this, I'm going to have to go back a bit in time and understand a bit the context in which I was doing my PhD. So the subject was looking at binary patches within, or finding if a security patches has been applied to a binary. And for this, you're looking at static analysis, and you're looking at thousands of, hundreds of binaries. So you need to find ways to scale a bit your analysis and how to do some analysis on disassembled binaries. And why are we actually talking about binary analysis? It's mostly because when you're in the wild, you don't usually have the source code. So part of the world is now running on a closed source system, which is not something that we're super happy about, but never mind. So when you have this, not the source code, the only thing you get is a binary code, and you have to look at the binary. The problem is how you make sense of this chunk of bytes, and how do you know that is either data, code, or random junk. And for this, since it's hard or impossible to do it by hand, you use something called disassemblers. So there is it's tools that have been developed to make sense of this junk or this chunk of bytes. But disassembling is a hard problem, so you have to understand the difference between code and data. You have to understand what is the control flow, recover the references between all of this, and also find function boundaries, which is even harder because it's a code source construct. And if you're not if you want to know more about this subject, there is a nice paper, Binary Code is Not Easy, that has been published in 2016 and highlights some of the problems. So since it's a hard problem, there have been a lot of different tools that have been published to do this, and we can divide them in two categories. So the first one, the commercial one, so I'm talking about Binary Ninja, IDA, and Jeb, for example, which have a professional support, but and rather expensive license, so it's hard to buy them if you're just an hobbyist. And you have the open source ones. So for example, Guidewire, Wadawe, Readzin, which are free to use, extensible, but maybe lack some support. I won't enter this debate yet right now. So actually, the most known of them is IDA Pro, which is a commercial one, which is rather old, about 30 years old now, and which support like 60 different architecture and processors, and which is very, very expensive. So it's hard to buy a license if you're on your own. But sadly, it's still one of the best, even the best disassembler in town. So if you want to do something, you kind of have to use it. And if you don't trust me on this, we published a blog post in 2019 comparing different disassemblers, and it still had the best results on x86 and most architecture. So if you want to automating your analysis, and I'm going back to where I started this talk, you have to use some kind of scripting within your tool. And for IDA, there is 3 different options. The first one is IDC, which has been deprecated, but was kind of a C-like language, and it was hard to use. Then you have the C++ SDK, and the C++ SDK is, well, most of the functions of the tool are exposed, but has a poor documentation, while it's still rather fast if you want to develop a plugin. You can get plugin with rather large performances, but it's a bit of a struggle. And finally, they introduced a few years ago IDA Python, which started as a plugin, but now is official, and it's Python bindings on top of the C++ SDK. So not all of the SDK is sadly exposed, but it's best if you want to prototype and if you want to do some quick scripting usage, then it's a nice way of doing it. However, scripting is limits, especially when you are stuck within IDA. So when you're using, you can only script do script for a single binary, and you have to be within IDA. But if you want to look at hundreds or thousands of binaries, you want to do something more on how to programmatically manipulate the disassembly kind of offline. And that's why binary exporters have been introduced, and now you're getting to see where I was trying to head to. So a binary exporter is something like a standalone file that you generate from the disassembly and then you can use outside of your disassemblers. So you just generate it once, and then you can close your disassembler, throw it to the bin, and then you still have all the results and the intelligence of your tool without any of its problems. So you can use export for a lot of things. For example, you can obviously query the disassembly, but that was something that you could do also within IDA. But you can also use it anywhere on a computer that does not have IDA. You can share the disassembly and so on. You can load a few binaries side by side and do the same queries on the two binaries, which is not possible if you're stuck inside your disassemblers. You can write scripts that are not dependent on a disassembler's version, and you can have a stable API, but you lose the interactivity. So if you want to, let's say, rename stuff and so on, and then and you reload your binary within your disassembler, then it gets lost. So that's some downside. There have been some exporters that have been introduced. The most famous one is BinExport, which has been developed by Dynamics for BinDiff. So Dynamics has been acquired by Google a few years ago, but to make BinDiff work, they actually export the binary using BinExport, and they load it within BinDiff. There is also the official GuideWare plugin for IDA, which exports a project from GuideWare to import it into GuideWare. And there is also something from 12 bits, an exporter from Maxima. But, well, all this IDA plugin have also some GuideWare counterparts. So BinExport has an official port now, and GuideWare also export a built-in kind of exporter, but most of these exporters have some limitations. The first one is they're not made to be manipulated outside of the disassembler, so you're lacking bindings. It does not always export the information you're interested into, so you kind of struggle. And then they're not compact, which is kind of a problem, and we're going to see why just in a while. So imagine why compactness matter. The first thing is if you're having a data set of 100 or 1,000 of binaries, it takes some weight. And if you start to run IDA on them, well, it takes time. And then the IDBs, so the file generated by IDA containing the disassembly's result, is quite large. And so we did this test with my intern on 2,000 libraries of OpenSSL, and we had about 6 hours of disassembly, and it took from 1.5 gigabytes of binaries about 25 gigabytes of storage, and it was only a tenth of the dataset. So you're going to see how much space it takes on disk, so it's hard to manipulate large binaries dataset and so on. And that's why Quokka comes into mind. So Quokka is a IDA plugin with a DALI generated logo. So it tries to export as much data as possible from the disassembly. It's quite efficient because we don't want to spend too many time exporting the data, otherwise it's unusable. And it's tried to be compact to alleviate the problem I mentioned earlier. So it's open source, obviously, and it's available on Quark's Lab GitHub. So to be a bit more specific, Quokka is an IDA plugin, so it has been written in C++, sadly, and to be efficient, it generates a protobuf for the exports, and the protobuf is a standalone file that you can query using the Python bindings. And if you're into, I don't know, PHP, then you could probably write some PHP bindings on top of protobuf. And so the tool is mostly exposing this API, and you can manipulate it outside of your disassemblers. So when I'm saying Quokka tries to export everything, it only tries to do it because it's kind of hard to. So there is a program layout. You know where is your code, your data, where is junk, and so on. So it's the top bar in IDA for those who are familiar with the tool. Every data, their types, their address, and their values, if needed. The graphs that have been generated by IDA. So either the call graph, the control flow graph, and so on. You also get the code information, so not only the functions, the blocks, and the instruction, but also the type, the mnemonics, and so on. And finally, every analysis result you already put inside IDA are also exported. So if you decided to comment somewhere, then it's also exported. And if you decided to rename some part with structures and enumeration, they are also there. So let me have a small break here. Never mind. Okay, so when I say Quokka is compact, so here's a comparison on two different binaries for either TS3 server and LLVM opt, which are random binaries I found on my computer. So if you look at the binary here, the first one, that's a size of 1, and then the IDB is 7 times bigger, been exported in something like 3 times bigger than the original binary, and Quokka is twice as big as the original binary, which is like a 3 times prediction over IDA. And then for LLVM opt, which is an even larger binary, you get, it's 9 times bigger as the IDB, and Quokka is like 3 times bigger as the original binary, which is a nice trade-off because you can drop the IDB and then you only have like 4 times your initial binary instead of 10 times when you want to manipulate them. And when we say that Quokka is fast, so let's compare it to BinExport. So the big blue bars are the IDA time for the disassembly, which is like the most important one. And then you add only the export time. So for BinExport, it's about 20% of the total time, while Quokka adds only about 8 to 10% of analysis time, which is much more manageable if you want to do it on a large scale. And then how to use the tool. So it's first an IDA plugin. So you have to install it using IDA. And since you want to have, to be efficient, you can use the IDA T version, which doesn't spawn a graphic interface, and you just use it in the command line with the Quokka auto parameters, or you can do it directly from the bindings by just asking to generate it with the from binary option. And this is the only step where you are required to get an IDA license. So, and then you can ask a friend if he has one, and then I get it. And finally, you get an export file, which is just a protobuf file, and you can use it without any other IDA version. And that's a small snippet on how to use the tool when you have your export. So you just get a program class in Python, and then you can manipulate it with, I would like to think, Zen defaults compared to the IDA API, but that's maybe I'm a bit biased because that's what I wrote. But when you're looking at the original Python scripting of IDA, that's something that looks a bit more sane. Let's talk about some demos because otherwise it's going to be a bit boring. So the first one is something that I was interested into because we are looking at some papers on machine learning, and most of these papers have some kind of feature extraction part. So let's take this context where you have this new shiny tool and you want to test it on some data set. But the problem is you need to extract, let's say, features from every function from every binary in your data set. So you have two options. The first one, if you don't have any exporter, is you're just stuck within IDA. So you write IDA scripts, and it's a bit painful, and you have to make sure they work for your IDA version. And if IDA version change in the middle, then you have to rewrite them, or you have to keep your old version, or you have a nice exporter, and you just have to write a simple script, and it works better. So for this example, I'm going to take how machine learning is solving the binary function similarity problem paper, which has been published in Usenix 2022 by people from Cisco Talos Lab, which is super good if you're interested in this kind of paper because they compare a lot of different approaches in machine learning and how they compare when looking at similar functions. And for all this paper, they had to write a features extractions for every function in the binary dataset, and they did it using IDA So they have hundreds, well, not hundreds, but a lot of IDA within their dataset on GitHub, and you can look at them because they're quite nicely done. But let's see how we can do this without using at all IDA API. And for this, like this. Okay. Perfect. Okay, so let's first import Quokka, and then we can load the program. So it's going to load it directly. And then we get the program that has been loaded. So this one is a simple cubic QuackMe that you can find also in the repo if you're interested. So let's go and explore what are the functions within the program. So we just get their name and their address, and there are some of them, and we can see that there are some levels. So it's a QuackMe, and there are some levels, so that makes sense. So let's take the first one, level 0. And look at how big is it. So it has 7 basic blocks, and we can try to now export some basic block features. So let's first look at every instruction in the first block of this function, and we get the instruction address and the capstone binding, the capstone disassembly for this instruction, because Quokka also provides capstones bindings. So you get all this instruction, and you see that it's just regular x86 code that are just loading and moving data around. So now, in the paper, they were looking for mnemonic classification. So to know if, for example, the mover mnemonic is something that is related to the stack or not. So they did this whole architecture mapping mnemonic mapping, which is quite a nice job. So for example, all the mnemonics in x86 that touch the stack, according to them, are those ones. But we're going to use it just because they want to classify the mnemonics. So let's write a function to export the basic block features. So first we get all the mnemonics, then we get the architecture of the program, and then we look at how big is it, what kind of constant it has, what kind of strings are included into, how many of them there is. So I'm not inventing this. They actually features they used in the paper. And on this one, it's how many mnemonics are using arithmetic features, and they did all of the others, but for brevity reasons, I don't put them all of here. And let's go further. So let's check if it works, and it's not just random code. So we see that we still have our basic block size, the strings that are used here. You have the what's the flag and something that looks like a flag, so maybe that's something to look at, and then other things. So now we can continue with function level features and what kind of features are exported. So first we get all the features for the block, and then we get all the features for the node, the age, by looking at the CFG of the functions. And then we export the number of nodes, the number of edges, and so on. And we get also our basic block features. And if we do this, and we can test it on our function to see if it works. And we get everything for every block in the function. So that is working. And now if you can just wrap it up and have it within your simple feature extractor for your binary program that has been done in like 2 minutes and 30 seconds, because I'm typing kind of super fast, and you get your JSON file in your repository, which is just there. And it's the cubic QuackMe JSON here. Okay, so let's go back here. So that was the first demo. And now a second one, which is a bit more interesting or different. And I like something that we can do with Quokka and such exporters. And that's actually an idea from a colleague of mine. So we had this Bionic file, which is a C library used in Android, and it has some changes with the classic libc you find on Unix system, and one of them is the user UID mapping is embedded within the binary, so you don't have the etc password file anymore. And the task he gave us was how to extract the mapping from the binary. And for this, we're going to use a simple strategy. So first, we're going to find a function that is using this user table. A second is going to, within this function, find the data references to this user table. Then look at, identify the table boundaries and read one entry, and then repeat until we have read the whole table. So first, the function using the user table, we can look at, for example, get pwUID, which is a function that returns a pointer containing a structure and so on, that actually looks at the data user mapping, and then just returns something related to the user ID. Then if we look at the code within IDA for this function, we see there is the data reference to the Android IDs. So we got the function correctly, and then we know that there is already a data references in the beginning of this function, so it's going to be easy. Then we identify the table boundaries. So for brevity reasons, we just say we use an heuristic, and then we can look at how can we read an entry, and we see that if we're looking at the source code of Bionic, we see that the Android IDs are a name, so it's a pointer to a string, and then a simple D word for UID. And finally, we can repeat until we get to the end of the table. So let's do like this. Let's keep this on, and then, okay. Oh, okay. Maybe we can do this. No. Okay, let's clear the screen. So, okay, so let's import Quokka first, like usual, and then let's load our libc that is already exported. So then we get the program that has been loaded. Then we want to look at a function, so let's look at the documentation of the get function. And since we're using IPython, you get the documentation for free in your shell, so it's super cool to prototype. So the get function takes a name as a parameter and approximative, so if we know the exact name, we can use this parameter. So that's exactly what we're going to do. So we are looking at the get pwUID function, and we found it. And now we can look at the data references within this function. So we are at step 2 here. So let's print all the data that are used within this function, their type and their address, because we are going to need them. And we see that there is 4 data. The first one and the last one are not named, but the 2 in the middle are the Android IDs table we are interested in. Then we can check what is this. We know that this Android ID table starts with a string. So if we are looking at a string in this for this data, we should actually read some username, and we see that we get the camera server UID, which is something nice. And then let's read the first user, so the mapping between the string and the ID. So we know that it's a table in C, so it's contiguous in memory, and then we have either the first is a pointer to a string, and then at +4 is going to be the address of the UID, so we can just get the value here, and that's exactly what's happened. So camera server has UID 1047, and then we can simply explain our heuristic to detect the end of the table. So we know it's going to be a table in C, And in this code, there is no references in the middle, code references in the middle of this table. So we iterate this contiguous chunk of memory until we find the code references. And that's something that is super easy to do with Quokka. So we see that the second user has no code references because it's not yet the end of the table. And there would have been other ways to do it, like finding, for example, in the function, the comparison until the max UID or the number of entries because it's statically embedded, but that's one way to do it. The user ID is read simply by using the read data function that takes an address and a size, so a double word here. And then we can wrap everything up and get the whole user table. So we start at the first element. And since we already have the first user, we get the next point. And then we continue until we find code references. And we find our first username, the user ID, we print them, and we append them to our table, and we increment our counter, and we iterate over this. So everything has been done without even touching the IDB, except for generating the export file. And that concludes the presentation. So first, what is yet to be, what needs to be done in the tool. So it's nice, but it's not complete yet. So there is no export of the types, which is a pain because it could be super nice to have them. And there are some other things that could be improved. And if we wanted to go a bit further, so you could actually export other disassemblers like GreHack, which has a nice API, even if it's in Java. And you could try to export decompiled information because at this moment we are only interested in the disassembly part. And we could integrate other tools like, let's say I want to get a context, like a Triton context for a function or so on. And that's all for me. So if you have any questions, don't hesitate. And then.
Thank you, Alexei. I really appreciate your talk and the fact that you took in consideration most of the comments that we made during the review. So I have no question now. Are there any questions? Oh. J'ai essayé de pas tomber. Oops.
Hello, thanks for the presentation. So as you said, it's kind of only compatible with IDA for now. Are there any plans to make it compatible with, I don't know, Gaidra, Radar 2 or anything else?
The problem of this is, as you're looking at the whole API of the disassembler, so since you have to export most of the thing, you have to look at the whole API, and maintaining one tool is hard, since even IDA changes its compatibility sometimes, and if you look at the plugin code, there starts to be fiddle with defines and so on. So maintaining it for another tool that I'm not using is kind of hard, but if someone is willing, like is using this and find it super interesting, I'm more than happy to help getting on board on this. But I don't think I have the skills in Java to do it, for example, for Gaidra, and I don't think other disassemblers could do the trick because they're lacking some features.
Okay, thanks. Any other question? All right, we're going to be thanking Alexei again.